Hello everyone, welcome to the first linear algebra lecture. So I'd like to begin with this quote from semi-famous mathematician Raoul Barthes, which he said that 80% of mathematics is linear algebra, which is definitely true. Linear algebra forms the foundation of a lot of concepts in mathematics, and you'll be using it a lot in your data analyses as it basically just shows up in a lot of places because the concepts that underlie linear algebra are very general and very applicable to many real-world problems. So let's begin. Linear algebra is essentially the study of objects called vector spaces. The idea of a vector space is very general, so I'd like to introduce vector spaces in a very general way, and the fact that they are so general is precisely why linear algebra has become so useful. All right, so to begin, let's say I have a set of objects here, just random objects. I have circle, triangle, and star. Then I can build a vector space out of them. A vector space is a set of objects that I can add together and multiply by numbers. So if I take these things and I multiply them by numbers, whatever that means, so I have A times circle, B times triangle, C times star, where A, B, and C are arbitrary numbers, and I form I add these together, whatever this object is also in my vector space. So the vector space is the set of the vector space built out of these objects is the set of all of these sorts of combinations of them. And when I have numbers multiplied by objects and I add them together, this combination is called a linear combination. So vector spaces are very general, and you can build them out of almost anything, but what are some of the more common vector spaces that you will encounter in your lives? Well, you may have seen some of these before. The most common one is definitely the set of vector spaces Rn. So this is the set of all n-element real-valued vectors. It's kind of denoted in this way. You've probably seen before where I have n numbers arranged in a column like this. So x1, x2, x3 are just real numbers. I can extend this to form the vector space Cn, which is the set of all n-element complex-valued vectors. And some other vector spaces that you might encounter include this one here, which is a little bit complicated. You won't need to worry about the details, but the vector space L2 between 0 and 1. This is the set of all sort of functions on the intervals 0 and 1. And this is a vector space as well, and it's important because this is the vector space in which Fourier analysis occurs. Again, you won't need to know the details, but it's helpful to be aware that, because we will be covering Fourier analysis, that basically everything we do in the second half of this class builds on the ideas from linear algebra. There's always an underlying vector space. So here's an example of those linear combinations in R3. So R3 is the space of 3-element vectors. Here's an example: 1, 2, 3, 4, minus 2, 3. And I can add these vectors together. And to do that, I just add each of the elements. So 4 plus 1 is 5. 2 minus 2 is 0, 3 plus 3 is 6. I can also take a vector and multiply it by any number, and I do that by just multiplying each component by that number. So I get 1 pi, 2 pi, 3 pi in this example. So vectors have a geometric interpretation, and I'm only going to spend a little bit of time on this because it's helpful to build intuition, but when we start working in higher dimensional vector spaces, you actually can't visualize them. However, what you can do is try to reduce the problem down to visualizing the problem in a space that you can visualize, like 1, 2, or 3-dimensional spaces, and then extrapolate from there. So in this picture, I have two vector spaces living in the vector space R2. I have two vectors living in the vector space R2. Scalar multiplication can be interpreted as just extending the length of these vectors by some constant quantity. And here it's A. Addition of these vectors is geometrically what you do is you take a vector and you stick the other vector at the end of that vector and you find out where you end up. So this green arrow is the vector that I get from adding u and v. And I can add u and v by taking u and putting v on the end of it and seeing which point I end up at, or taking v and putting u at the end of it. They're the same. A central concept in linear algebra is the idea of linear independence. So linear independence kind of means intuitively that that vectors point in different directions. So you only talk about linear independence with a set of vectors. And the definition of it is if I have a set of vectors here, v1 through vn, then I call them linearly independent if and only if the only solution to this equation, which is a linear combination of these n vectors, where I have a1 times v1 plus a2 times v2 plus an times vn, the only solution to this being 0 is if all of the constants here are 0. I'll give you an example of this, see how that works in the next slide, but intuitively, in this example, in this picture, here v and u are linearly independent because u and v point in different directions. I can't get to v by going anywhere along u. However, in this example, they are linearly dependent because I can clearly get to u by going along v, and I can get to v by going along u. So a vector is linearly dependent on a set of other vectors if the given vector is a linear combination of the other vectors. How does this work? All right, let's see if we can compute whether this set of vectors are linearly dependent. Well, we know that if we add 1, 2, 3 and 4 minus 2, 3, we get 5, 0, 6, which is our third vectors. So these vectors are not linearly independent because I can form a linear combination of them, here 1, 2, 3, plus 4 minus 2, 3, minus 5, 0, 6, and that gives me 0. So there is a non-trivial linear combination of these vectors that gives me 0, so this set of vectors would be said to be linearly dependent. Well, what about the other case of linear independence? Let's consider these three vectors. To check for linear independence, I form the most general linear combination of these three vectors that I can, and I see if I can get 0 from this linear combination. So to form the linear combination, I multiply each vector by its own constant, so I have a1 times the first vector, a2 times the second vector, and a3 times the third vector. And when I compute this sum, I get this vector, which would be a1 minus a2, 6a3. Remember, these are just arbitrary numbers. Now, I asked the question, when is this vector that I get from this linear combination of these three vectors 0? And you can see that the only way that this would happen is if a1 equals 0, a2 equals 0, and a3 equals 0. Since they're all 0, then these vectors are called linearly independent. A related concept is the idea of the span. So the span of a set of vectors is the set of all linear combinations of those vectors. So let's compute the span of this previous example. The span of these three vectors would be the set of all vectors in R3 that are of the form a constant times the first vector, a constant times the second vector, and a constant times the third vector. We've already computed this, so it's all the vectors of the form a1 minus a2 and 6a3, where a1, a2, and a3 are arbitrary numbers. Notice that I can write any vector in R3 in this form. So we say that the span of these three vectors is all of R3. Spans have a geometric interpretation. So the span of a single vector would be a line through the origin because it's just a number times that vector, which means I'm scaling that vector by a number. So I'm just moving along a line in the direction of that vector. The span of two linearly independent vectors is a plane because I have two independent directions I can move, and the plane is a two-dimensional object. The span of three linearly independent vectors would be a 3D space. We saw that in the previous example where I have three linearly independent vectors, and the span of those vectors was all of R3, which is a three-dimensional space. However, this relates to linear dependence in the following way. If I have two linearly dependent vectors, then the span of those two vectors is just a line, because I only have one independent direction I can move. Similarly, the span of three linearly dependent vectors is either a line or a plane. It would be a line if I only have one independent direction I can move, which would be if all three vectors pointed in the same direction, or it would be a plane if I had two vectors pointing in the same direction and one vector pointing in a different direction. So the span, let's do a different example. The span of these four vectors would be given by forming the most general linear combination of these four vectors, and you can work that out for yourself, but you end up getting this expression, a1 minus a2 plus 4a4, and 6a3. Now notice that 0, 4, 0 is the same as minus 4 times 0 minus 1, 0. So these vectors are not linearly independent. However, the span is still all of R3 because I can write any vector in R3 in this form. So this leads to the concept of a basis, which is a fundamental concept in linear algebra. Any vector space has a basis. So a basis for a vector space is a set of linearly independent vectors that span the entire vector space. What this means is that any vector in a vector space can be written uniquely as a linear combination of basis vectors. And the number of vectors in a basis is called the dimension of the vector space. So the prototypical, any vector space can have an infinite number of bases. However, most often it makes sense to work in sort of a standard basis, and since you're going to be working most often in Rn, we talk about the standard basis for Rn. And the standard basis is just given by this set of n vectors, where I have a 1 in each successive component. So I have a 1 in the first component, 0 is elsewhere, a 1 in the second component, 0 is elsewhere, all the way up to the 1 in the nth component. We've been implicitly using this basis because if I take a vector like that I've been writing at 6, minus 2, and 1, I can see that I can write it as a linear combination of these basis vectors. So these components just represent the coefficients of each of the basis vectors. So here I have 6 times 1 gives me 6, minus 2 times 1 gives me minus 2, and 1 times 1 gives me 1. So typically, a basis, whatever it is denoted by e sub 1, e sub 2, all the way up to e sub n. This is just the notation for the basis vectors. An important operation that one can do to vectors is called the inner product, or the dot product, or the scalar product. It goes under all three of these names relatively frequently, so it's important to be familiar with all of the terms. But essentially, the dot product maps two vectors to a real number. So it's an operation where I can give it two vectors and I get a real number output. So let's see how this works. Let e sub 1, e sub 2 to e sub n be the standard basis. Then I can take two vectors, v and w, and I can write them as a linear combination of basis vectors, where my components are v1, v2 up to vn, and w1, w2 up to wn. The dot product is obtained by taking each of the components between the two vectors and multiplying them and then adding them all up. So I take the first component of v times the first component of w, so I get v1 times w1, and I add to it v2 plus times w2 plus all the way up to vn times wn. Since these are components, these are just numbers, so all I have here is a sum of real numbers, so I get a real number output. Let's do an example. So here in R2 I have two vectors, 1, 4, and 2, minus 3. The dot product is obtained by taking the first component of the first one times the second component of the second one, so 1 times 2, and adding to it the second component of the first one, 4, times the second component of the second one, minus 3. So I get 1 times 2 plus 4 times minus 3, which is 2 minus 12, which gives me negative 10. So that's how the dot product works. Related to the dot product is this concept called the norm. The norm is also known as the length. So how do we measure the length of a vector? Well, excuse me. This comes from taking the dot product of a vector with itself. So when we dot product a vector with itself, we just multiply the first component by itself, the second component by itself, the nth component by itself, and add them all up. So we get v1 squared plus v2 squared all the way up to vn squared. And we denote this as the norm of v, which is these two vertical lines, squared. So the norm, or the length of a vector, is the square root of the dot product of that vector with itself, and it's denoted with these two vertical lines. Let's do an example or two. Let's compute the norm of the vector 1, 0. So we take the dot product of it with itself, which gives us 1 times 1 plus 0 times 0. So we get the norm squared is 1, but the square root of 1 is 1, so the length of the vector 1, 0 is 1, which makes sense. A vector with norm 1 is called a unit vector. It's some terminology that you should be aware of. Let's do a different example. Here we have the vector 2, 0. The dot product of this vector with itself is 2 times 2 plus 0 times 0, which gives us 4. So the norm squared of 2, 0 is 4, which means that the norm of this vector 2, 0 is the square root of 4, which is 2. So the length of this vector 2, 0 is 2, which makes sense. So I won't prove that this relationship holds, but a useful way to picture the dot product is using this alternative formula for the dot product. So here I have two vectors, A and B, and I want to compute their dot product. Another way to do it is to take the length of A times the length of B and multiply that by the cosine of the angle between A and B. So let's look at a picture. Here we have A, and here we have B. You see they point in different directions, so there is an angle between them. So the dot product of these two vectors would be the length of A times the length of B times the cosine of this angle. And we can see now what the dot product is really saying. The dot product allows you to measure sort of how much of one vector is accounted for by the other vector. This length along B here is given by A dot B divided by the length of B. So the length of A times cosine of theta. And you'll remember that this gives us this component of the vector. So it is measuring basically how similar A is to B. If we look at this cosine term, we can come up with some classifications of pairs of vectors based on the quantity of the value of their dot product. When theta is 0, cosine is 1. It's at its maximum. So the dot product is at a maximum when theta equals 0. When theta equals 0, that means the vectors point in the same direction. And so the dot product is a maximum. And we say that the two vectors are parallel, which makes sense because they go in the same direction. When theta equals pi, which means 180 degrees, A is pointing in the complete opposite direction of B. So this is when the dot product is a minimum because cosine of pi is minus 1. And the length of A and the length of B both have to be positive. So this gives us a negative quantity and it's the minimum of the dot product. So when theta equals pi, the two vectors have opposite direction. A third case is so special that it warrants its own slide, and it's important to remember this. So when the dot product is 0, we say that two vectors are orthogonal. And orthogonality is a very, very important concept from linear algebra. What does this mean? Well, when the dot product is 0, remember that the length of A has to be non-zero, the length of B has to be non-zero, and so that means that the cosine of theta has to be 0. Cosine of theta is 0 when theta is pi over 2, or 90 degrees. So the dot product of two vectors is 0 precisely when the vectors are separated by 90 degrees. They're at right angles to each other. More generally, any pair of vectors in any vector space whose dot product is 0 are called orthogonal, even with the concept of being at a right angle doesn't make a whole lot of sense. It's a generalization of this concept. So what does this mean in pictures? Well, at the top we have two orthogonal vectors, and we can see that there's a right angle between them. And basically, what you'll notice is that in this case, V tells me nothing about U, because V, I can go along V, and I go along no amount of U. Similarly, if I go along U, I go nowhere along V. We can contrast this to the case when the vectors are not orthogonal, because going along A here goes along B a little bit as well. You can see A kind of points in a sort of similar direction to B. So these are not orthogonal, but when two vectors are orthogonal, they go in completely different directions. And this kind of represents a minimum redundancy. U tells me nothing about V and vice versa. So we can combine the concepts of orthogonality, the unit vectors, and a basis to obtain something called an orthonormal basis. And this is just a concept that you should be familiar with. If all of the vectors in a basis are mutually orthogonal, that means if I take any pair of them and the dot product of the elements in that pair is 0, and each vector, individual vector, has norm 1, then we say that this basis is an orthonormal basis. An example of an orthonormal basis is one that we're already familiar with, in that the standard basis of Rn is orthonormal. It might be helpful for you to check that this is the case by looking at this, taking the standard basis and computing the pairwise dot products to seeing that they are 0, and then computing all the norms and showing that they are 1. Alright, so from vectors we will move to matrices. A matrix is simply an array of numbers. Typically, the size of a matrix is reported as the number of rows by the number of columns. So here we have 4 rows, and here we have 4 columns. So this is a 4 by 4 matrix. Here are some examples of some other matrices with different sizes. 2 by 3, 3 by 3, 2 by 2. And you'll notice that vectors are just n by 1 or 1 by n matrices. So by studying matrices, we study vectors at the same time. Something you can do with matrices is that you can multiply them together, but matrix multiplication is a little tricky and not like multiplying 2 numbers together. So if I have a matrix A and a matrix B, I can get matrix AB only if the number of columns of the matrix on the left, which in this case is A is to the left of B, equals the number of rows of the matrix on the right, which is B. B is to the right of A. So if A is 2 by 3 and B is 3 by 8, then I can form the matrix product A times B, because 3 here is equal to 3 here. So I'd get an output matrix, a result that is a 2 by 8 matrix. However, because 8 does not equal 2, I cannot perform the multiplication B times A. So the order matters. We say that matrix multiplication is not commutative. It's very important to remember that the order of matrix multiplication matters. Sometimes, if I have square matrices, then I can do A times B and B times A. However, in general, A times B will not equal B times A. So the order matters. This is very important. How is matrix multiplication defined? Well, it's defined for, so if we have a matrix A and we want to multiply it by a vector, which remember is just an n by 1 matrix, then we can define it with this formula, which means so the what this formula represents is I take the ith, to get the ith component of my resultant vector W, I take the ith row of A, and I take the dot product of that ith row with the jth column of V. So J only has 1 column here. So I have basically to get the output, I take the vector 1 minus 2 and I dot it with minus 1, 1, and that gives me minus 3. And then I take the dot product of minus 2, minus 3, and I dot product that with minus 1, 1, and that gives me minus 1. So you can work through this example to see how this works. Minus 1 times the first column, 1 times the second column, add them together, and I get minus 3, minus 1. But how does this work when I have 2 matrices where 1 isn't a vector? Well, in general, to compute the ith row and kth column element of the product of 2 matrices, I take the ith row of the matrix on the left, which is A, and I compute the dot product of the ith row with the jth column of matrix B. So here it is in pictures. To compute the 1, 1 entry, which is the first row and first column, I dot product the first row of matrix A, 1, 2, 3, with the first column of matrix B, 7, 9, 11. And I get 58. You can see why there are restrictions on the size of the matrices, because I have to have the same number of elements here, same number of columns, as the number of rows to compute the dot product. Otherwise, I'd have stuff left over. That wouldn't make sense. Here is another example. And you can work this out on your own if you choose. To compute A times B, to get this first element, I would take the dot product of 3, 2 with 3, 4, which is represented here, and that gives me 17. To get row 1, column 2, I take row 1 of matrix A, which is 3, 2, and I dot product it with the second column of B, which is 2 minus 2. So I get this here, which is 2, and so on and so forth. But now notice, if I tried to compute BA, I would have 3 columns of B attempting to be dot product with the 2 rows of A. That doesn't make sense. So I cannot compute BA. It does not exist. What happens if I have square matrices? Then I can compute both A and B and BA because they have the same dimensions. So this would be 2 by 2, this would be 2 by 2. You would think that AB would equal to BA, but this is not the case. Here, if I take A on the left and B on the right, I get this answer. But if I take B on the left and A on the right, I get a different answer. So the order matters, and this is important to remember when you're using matrices in MATLAB, for example. Because if you're setting up something, you have to pay attention to the order in which you're multiplying matrices. There's a special matrix called the identity matrix, and it has to be a square matrix. And it's given by just having 1s on the diagonal of the matrix. So you can see here the 2 by 2 identity matrix just has 1s on the diagonal. The 3 by 3 has 1s here. And the n by n has 1s here. This is the matrix analog of the number 1, because if I had a 1 by 1 matrix, then my matrix I1 would be just the number 1. The property of this that's special is that multiplying anything with an identity matrix will give you that same thing. So if I had a vector here, and I multiplied it by I3, I would get that vector out again. Furthermore, the identity matrix does commute with any matrix, which means it doesn't matter the order in which you multiply the identity matrix. We will refer to the identity matrix of dimension n, which means it has n by n. It's an n by n matrix as ID sub n. So now that we have the identity matrix, we can talk about something called the matrix inverse. As you're probably aware, all real numbers have a multiplicative inverse, given by, if I have a real number x, it's given by 1 over x. The property that defines this is, given a number x, finding another number such that x times this other number gives me 1. So that's the definition of the multiplicative inverse. You might ask, does a similar notion hold for matrices? Yes, it does. And this is important because inverting a matrix is kind of like solving equations. So when you use linear algebra to set up a problem to look for a solution, you end up kind of trying to find matrix inverses. Excuse me. But there are some caveats to computing a matrix inverse. Suppose that we have two matrices A and B. If A times B equals B times A equals the identity matrix, then we say that B is A inverse, and vice versa, that A is B inverse. If V is a vector, and W is B times V, then A times W would be A times B times V, which is B times A times V, because the inverse exists. I'm postulating that the inverse exists. So it would be identity matrix times V, which just gives me V again. So in a sense, A undoes the transformation that B did. B turns my V vector into W. A turns my W vector back into V. That's what it means to have an inverse. Now, only square matrices can have inverses. And it might be helpful for you to take a moment to try to see if you can explain why that is the case. Furthermore, not every square matrix has an inverse. Let's give an example of what a matrix inverse would actually look like. So here I have the matrix 4, 7, 2, 6, and if I multiply it by this matrix, then I expand out the definition of matrix multiplication, and I compute each element, and I find that it equals the 2 by 2 identity matrix. So this matrix and this matrix are inverse of each other. I mentioned not all square matrices have inverses. A matrix has an inverse if and only if a quantity called the determinant is non-zero. The determinant is a complicated quantity to compute. You pretty much never have to compute it, but you should be aware that that's kind of what dictates whether a matrix has an inverse or not. So how do you go about using the matrix inverse? Well, oftentimes, and we'll see this come up many times, your problem, whatever it is, data analysis of some kind, can be expressed in the following form, where y, x, and b are vectors and a is a matrix. And you know y, and you want to find x. For example, linear regression is of this form. In order to compute x in terms of y, you would use the matrix inverse. First, you would subtract b from both sides, and then you would multiply by A inverse, assuming that it exists on both sides, and then you get this expression for x. Now, when you're working with real data, sometimes A inverse will not exist. How do you move forward? Well, in the applications lecture, the second lecture, we'll talk about something called the pseudo inverse, which kind of lets you get around this restriction. You've already seen it before, actually, but we'll save that for the second lecture. In practice, it's very hard to compute a matrix inverse, and you'll never need to do it by hand. In fact, even though MATLAB can compute a matrix inverse, it's oftentimes inadvisable to do so directly. MATLAB has an expression a\y that you would use instead of computing inverse a times y, and this expression tells MATLAB that you're trying to compute the matrix inverse times a vector, and so MATLAB will use some more advanced techniques from linear algebra to compute this quantity much faster than computing the inverse of a and then multiplying that by y. So it's important to be aware of that. Another matrix operation that is important is the transpose. So the transpose of a matrix is denoted A with this t exponent, and it is obtained by simply exchanging rows for columns. So here I have row ABC, and when I transpose it, it becomes column ABC. In general, when I don't have square matrices, the transpose will turn an n by m matrix into an m by n matrix. Notice that the diagonal elements stay the same. So why matrices? We appear to have pulled matrices and matrix multiplication out of thin air, but where do they come from? Matrices come naturally when one considers transformations of vectors, called linear maps, and I think that this is actually the less abstract, more practical way to introduce matrices and matrix multiplication. So for this next part, you won't need to be able to reproduce these derivations for the class, but I believe that it will help immensely in understanding linear algebra if you try to follow along with them. So let's begin. What is a linear map? Well, you know, you're familiar with functions. So a function like x squared takes in a number and gives me the square of that number. So if I give the function 2, x squared will give me 2 squared, which is 4. A linear map is a function between vector spaces, which means that I give it a vector in one space and it gives me another vector in a possibly different space. But importantly, linear maps are functions that satisfy two conditions, outlined here. The first one states that the linear map acting on the sum of two vectors, v and w, is equal to the sum of the vector you get when you act on v with the linear map and the vector you get when you act on w with the linear map. The second condition states that if I have a constant times a vector, then the linear map of that constant times a vector is the same as that constant times the linear map acting on that vector. So let's see what the consequences of this are. If we have a vector written in some basis, so we have vector v here, written in the basis e1 through en, and I have its components a1, a2, a3 up to an, then if L is a linear map, we can see that L of v, and using these properties, can be written as a1 times L of e1, a2 times L of e2, a3 times L of e3, and so on. It's a good exercise to prove this relationship using the two conditions for a linear map. It's not hard. All you have to do is take this expression for v and plug it into each one of these conditions and to see what it gives you. So what does this mean? These are numbers, these are constants, and these are vectors. So all we need to know to evaluate a linear map on any vector is to know the value of the linear map on each basis element. L of E1, L of E2, L of En. But each one of these is a vector, because the linear map takes in a vector, which is this basis element, and it gives me a new vector. So if we write out the components of these resultant vectors in some basis, we get this representation, where this is the first component of the result of applying L to E1. This is the second component of the result of applying L to E1. This is the second component of applying L to E2, and so on and so forth. But check this out. This is a matrix. So this is where matrices come from. Matrices are the representation of linear maps. Matrices represent linear transformations between vector spaces. So each element of a matrix is a component of one of the results of applying a linear map to a basis element. So consider a linear map between the vector spaces Rn and Rm. We denote it this way. The name of our function is L, and it takes in as input vectors in Rn, and it gives us vectors in Rm. We've seen that it can be represented by this matrix. And in fact, this is an m by n matrix. So generally, the number of rows in your matrix is the dimension of your target space, or the space where your output lives, Rm. See, this is dimension m, and we have m rows. And then the number of columns is the dimension of our source space, Rn. So we have n columns. Now, how do matrix operations that we've studied look in this form? So let's consider the case of a matrix times a vector. Well, this is the formula from before. We write our vector v as the sum of a component times a basis vector, all the way up to n. And as we've seen, L of v is just a1 times L of e1, which this is a vector. This is in fact the first column of A. A2 times L of E2, which is the second column of A. A3 times L of E3, which is the third column of A. So you can see what this means. We take the jth element of V and we multiply it by the jth column of A. So the first element of V gets multiplied by the first column of A. And then I add all of these together. So the way to interpret this, we have a linear map, L, mapping Rn to Rm. So V here has n components, it lives in Rn. W here has m components, it lives in Rm. Okay, so what about matrix multiplication, where we multiply two matrices together? Well, in this view, this is interpreted as the composition of linear maps. What we mean by composition is that we perform we start with a vector, and we act on it with a linear map, and then we act on that result with another linear map. So suppose that we have two linear maps. We have phi, that maps Rn to Rm, and C, which maps Rk to Rl. When does it make sense to talk about the composition of these two maps? In other words, when does it make sense to act on a vector with phi and then act on the result with C? Well, notice that if I give phi a vector in Rn, I will get a vector in Rm out. But C expects a vector in Rk. So if k does not equal m, then the result of applying phi, which lives in Rm, doesn't live in the same space as as C expects its inputs. They're completely different spaces because, like, for example, R2 is not R3. So it doesn't make sense to talk about the composition of these two maps when k does not equal m. But if k equals m, then the output space of phi is the same as the input space of C. So I can compose these two maps by applying phi first and then C. And I write that as phi, you read this as C of phi. So I take a vector in Rn, I act on it with phi, and then I take that result and I act on it with C. And this maps Rn to Rl, because I go from Rn to Rm, which is the same as Rk, and I map that to Rl. So we have a new linear map, C of phi. How does this look when I write everything out? What does this look like as a matrix? Well, phi of c, kj, is equal to the kth row of c dot producted with the jth column of phi. Now where does this come from? Let's say I have a vector v and I act on it with phi to get a vector w. This means I perform this operation. So w equals phi of v. Now I act on w with c, which is given by this expression. See, these are the same things. I'm just working with c instead of phi and w instead of v. Now, what happens if I write out this equation, which told me what w is? I get this expression for the result. So I sum over I, the kth row of c, with the jth column of phi. I can rearrange the sums so they look like this. So this is now just a matrix indexed by k and j, like over here, and I get this expression for what the matrix representation of c composed with phi looks like. Now notice that this only makes sense if the number of elements here for this I equals the number of elements here for this I, but this is the ith. This represents the number of columns of c. This represents the number of rows of phi. So we can only perform this operation if the number of columns of c, which is on the left, equals the number of rows of phi, which is on the right, which is what we claimed before. So what does this look like as a matrix? Well, we've expressed that as this combination. So this is the formula for matrix multiplication. What if we try to do things in the opposite order? What if we wanted to act on a vector with c first and then phi? Well, remember how we've defined this. Phi maps Rn to Rm, c maps Rk to Rl. If n does not equal L, then phi of c doesn't make sense because c will take vectors in Rk, map them to Rl, but if n doesn't equal L, then these are different spaces, so phi can't operate on the vectors that c produces if L doesn't equal n. Okay, so that's the rundown of the basics of linear algebra, and these concepts we're going to use in the second lecture to build some applications out of them to see how you might use these ideas when analyzing data, especially neuroscience-related data. So we'll see you next time.